Welcome. Welcome to the Spring 2014 School of Earth Sciences Distinguished Lecture. Today's speaker is Professor Randall LeVeque. Randy is a Stanford PhD in computer science. He's spent most of his career at the University of Washington working on hyperbolic problems. Hyperbolic equations are the ones that govern wave propagation and related phenomenon. Those problems are characterized by the development and motion of very sharp features, discontinuities like shocks in fluids, where pressure and velocity, or in the case of tsunamis, the actual depth of the water changes very abruptly. Those abrupt transitions create lots of challenges for numerical modeling. And over the years, Randy has made some really fundamental contributions into the types of numerical methods that can be used to tackle those problems and give solutions that are both accurate and robust. For his work, he was awarded, he's become a fellow in the Society of Industrial and Applied Mathematics, as well as the American Mathematical Society. Randy has recently turned his attention towards the application of these methods to problems in geophysics, ranging from landslides and debris flows to volcanic eruptions and tsunami modeling. He's devoted a lot of attention and effort towards reproducible research and open source software. His code, which is very widely used, Clawpack, the component of it related to tsunami modeling has undergone extensive validation and verification tests through NOAA and has been being used for probabilistic tsunami hazard analysis for places even here in California like Crescent City. So today he's going to tell us about these numerical methods and about their application to some really fascinating problems in earth science. So please join me in welcoming Professor LeVeque.
So thanks very much, Eric, for that nice introduction. And thank you for inviting me here. It's always a great pleasure to get back to Stanford and see a lot of old friends and meet some new friends. So it's great to be here. So I'd like to talk about a variety of sort of hazard modeling problems and talk a bit more about some of the applications that we've been making of these methods, not get too much into the mathematics or algorithms, but I'll give you a flavor at least of the sort of algorithms that we use for adaptive mesh refinement, which is a very important component of a lot of what we're doing. The picture here on the front is motivated by the recent tragic landslide up in Washington State near Oso, Washington, just a few weeks ago. And one of the groups that I've been working with quite a bit over the last few years is at the USGS Cascades Volcano Observatory in Vancouver, Washington. And they've been in particular developing a debris flow code for modeling exactly this kind of event. And this is one of their simulations of that. I'll show some other things that they've been doing with that code, but this is kind of an outgrowth of the GeoClaw code that we've been developing originally for tsunami models. David George, who's now at CVO, Cascades Volcano Observatory, was originally working with me on tsunami modeling and has been developing this code further for a variety of other applications. So let me first talk a little bit about the debris flow problem. So at the Cascades Volcano Observatory, they're very interested in debris flows related to volcanic eruptions in particular. This is a picture of the remains of a debris flow after the eruption of Mount St. Helens in the early 1980s, when the glaciers that were on the mountain melted as the volcano erupted and sent a very large flow going down into the surrounding valleys. We have another volcano near Seattle, Mount Rainier, which is still an active volcano and will eventually erupt again. This is a telephoto zoom picture from Tacoma. It's not quite as close as it looks, but it's still dangerously close to quite a few inhabited areas around the Seattle-Tacoma area. In fact, this is a map of some of the past debris flows from previous eruptions of Mount Rainier. So Mount Rainier is down here, and there's a number of valleys where they've found remains of debris flows from previous eruptions. And there's a number of towns in these valleys, of course, and there's also the city of Tacoma is right in here. Seattle, the debris flow presumably wouldn't reach up to Seattle, but this is a very densely populated area down here. So there's a lot of interest in modeling things like debris flows in connection with volcanic eruptions. And as you can see here, this problem has a characteristic that's common to a lot of the things I'll talk about, which is that there's a very different length scales involved here. This is a large region that we're looking at, but the regions where the actual flow is often these fairly narrow valleys. And within those valleys, if you want to accurately model what might happen in such a debris flow, you need to have a very fine resolution grid to solve the numerical model of your model equations on. On the other hand, other areas where there are higher peaks, you know that there's not going to be any flow at all, so you don't need much resolution at all. And so ideally, you would like to have grids that are refined in the regions where you need them and that adapt to the flow as it's moving, so that you start with grids only around the volcano, and then they adaptively expand outwards as the flow advances. So that's a big part of what we've been working on in the software recently. So I'll show you one animation of another debris flow problem that I've been looking at recently. This is a big landslide that happened up on Mount Meager in British Columbia in 2010, where a big chunk of the mountain, 48 million cubic meters, let loose and went down the valley. This was an uninhabited valley, but it was still a pretty major event there. This I threw in just to show you, I'm not really going to talk too much about seismic modeling, but there's a lot of interest in looking at the seismic signals that are created by landslides like this. Kate Allstadt, who was a student at BU, is still a postdoc there, but is moving to the Cascades Volcano Observatory next year, is working in particular at modeling the seismic signals from landslides and looking at potential early warning systems, so that if a landslide starts, you can tell whether it's going to develop into a large-scale debris flow that might endanger people farther down in the valley. So this is an aerial view of this part of Mount Meager that collapsed and went down the valley. It's a little hard to see here, but it went down a hillside, and then it hit a valley here where it kind of split, and most of it went downstream, but some of it went up the valley in addition. It's a little easier to see what happens in the animation here. So here you can see the adaptive mesh refinement. We start with a very coarse grid where there's nothing happening. Then there's a finer grid that's refined by a factor of, maybe it's a factor of 6 or 8 in each direction. And then there's even finer grids where the grid lines aren't drawn that are actually sort of able to resolve the flow as it moves. And so every few time steps, we do a regridding on every grid level. You flag the points that need refinement according to some criterion, and then those flag points get clustered into rectangular patches, and you take a few time steps, and then you regrid, and this is done sort of recursively at all levels. So in this particular simulation, they only use 3 levels of refinement, but often for tsunami modeling, I'll show some results later where we use 6 or 7 levels so that you can start with very large grid cells on the ocean and zoom down to very small grid cells, a few meters on the side perhaps, and in a particular harbor that you're trying to model. So this is a comparison of the aerial photo that we saw before and the sort of final configuration after this flow. So this is a debris flow model that's been developed largely by Dick Iverson and Roger Denlinger and Dave George at the Cascades Volcano Observatory, and then implemented into the software. So it's something like the shallow water equations that we use for tsunami modeling. It's a depth averaged model where they keep track of the depth of the flow and velocities in 2 horizontal directions, momentum. But it's a more complicated rheology than just water, to take into account the fact that you have this complex fluid with some pore pressure. So the advantages, of course, of a depth average model is that we're solving 2-dimensional systems of partial differential equations rather than full 3-dimensional systems that you might think you need for modeling these 3-dimensional fluid dynamics problems. But you still need adaptive mesh refinement, even though it's a 2-dimensional problem. To do these things efficiently, you really need to be using adaptive refinement. Another big advantage of using a depth averaged equation is you don't have a free surface at the top. If you did full 3-dimensional Navier-Stokes equations or something, then you would have a free surface that would be moving. Here, one of our variables is the depth of the fluid, and so there is no sort of free surface boundary condition. Instead, you have just the depth and the horizontal momentum components averaged over each grid cell, for example. But there are lots of possible problems with this. It's not clear always that these depth averaged equations are accurate enough, and in some cases, you might want to switch from doing a depth averaged model to doing a full 3D flow for detailed analysis of some part of the flow. But it turns out that for a lot of problems, these depth-averaged equations give a pretty good approximation. There's other problems, as we saw in this video, as this flow moves out at the margins of the flow, the edges, you've got also a boundary. But as you might have noticed, we're always solving it on rectangular grids, or logically rectangular grids, maybe latitude, longitude grids on the sphere, but they're just rectangular grid patches. So we don't try to use a grid that conforms to the boundary of where the fluid is and change those grids. Instead, we just use rectangular grid patches, but each grid cell could be either wet or dry. So the boundary is simply where the interface is between wet cells and dry cells. So if you really zoom in, the boundary always looks like sort of a stair-step pattern, but if you've resolved well enough, then that's a pretty good approximation of where the edge of the fluid is. But that does give problems in implementing these methods. If you look at something like the partial differential equations that model the shallow water equations, say, or these other depth-averaged models, if you have a cell that's dry adjacent to a cell that's wet, then you've got an interface where you've got depth 0 on one side, non-zero on the other. You have to do something special to look at how the water spreads into a dry cell from a wet cell. You have to worry about cells drying out without the depth going negative. If the depth goes negative, typically things go wrong, especially since the wave speeds that we need to calculate go like the square root of GH for the shallow water equation. So if H is negative, you know it right away. So you have to put in various things to make sure that the algorithms remain robust. There's also problems in tsunamis that I won't say too much about, but you have this nice steady state of the ocean at rest before the tsunami happens, where you've got big variations in the seafloor bathymetry and therefore big variations in the depth of the water, but still nothing should be moving because the variations in hydrostatic pressure are balanced by variations in the bathymetry, which also come into the equations. And so you have to make sure you maintain that balance numerically. So I'm not going to go very much into the equations or the different aspects of the algorithm, but there's quite a bit that goes into making these algorithms work robustly on these sort of real-world problems. So the software that we've been developing, Eric mentioned Clawpack, which stands for Conservation Laws Package, because initially we were looking at hyperbolic systems of conservation laws, equations that model conservation of mass, momentum, and energy, for example. And there are various variants of this software that have kind of grown out of this, and one of them is this GeoClaw software, which started with Dave George's thesis work when he was working on tsunami modeling. So it was originally called Tsunami Claw, and then as we realized that it could be applied to lots of other things, we made it more general. So it's now called GeoClaw, and now actually they have a new version called DClaw for this debris flow code that they're developing at the USGS. For those who work with hyperbolic equations, the basic idea is that we're using finite volume methods with Riemann solvers, so that's a way of sort of taking the jump in depth and momentum between two cells and resolving that into a set of waves that can be used to update the cell averages on either side. And as I mentioned, you have to do various special things to deal with the problem that one cell might be dry and that you need to keep things well balanced when you have the steady state at rest that you need to maintain. So a lot of that is built into the software along with the adaptive mesh refinement. So it's been applied also to other things. I'll talk about tsunamis in a little bit, but it's also been used for storm surge problems. My former student now, Kyle Mandley, is at the University of Texas in Austin working with Clint Dawson's group on storm surge modeling. I'll show one of his simulations in a minute. Jiwon Kim, another student who just finished, was working on modeling submarine landslides, where we hope to eventually couple in some of this debris flow landslide modeling together with the tsunami modeling. So let me just say a little bit about uses of models for these sort of geophysical problems. So as the statistician George Box said quite famously, all models are wrong, but some are useful. So you have to always take any sort of modeling results with a grain of salt and ask whether the results that you're getting are really meaningful or not. But to a large extent, there are good models these days that can be very useful if they're used properly. And they've improved a lot in the past few decades for a number of reasons, partly because the geophysics is better understood, partly because there's a lot more data available which can be used to understand the geophysics better, but can also be used to calibrate the models and to test different sets of mathematical equations and see when they agree reasonably well with reality. So better mathematical models have been developed as a result of that. There's also been big improvements in numerical algorithms and, of course, greater computer power that allows us to solve these much bigger simulation problems. But one point I'd like to make is that even though computer power, of course, has grown exponentially, according to Moore's law, over the past several decades, the improvements in numerical algorithms are also equally important, in my view. This is a graph. It's about 10 years old now, so it doesn't go up to the present, but it shows from 1970 to 2000 the sort of exponential growth in computing power. This is a logarithmic scale, so you're seeing basically a factor of 10 to the fifth improvement in computing power over those 30 years. The top picture is over the same time period, the increases in our ability to solve a simple linear system, AX equals B, by different algorithmic advances over that same time period. So going from, say, sparse Gaussian elimination back in the 1970s to iterative methods like Gauss-Seidel, successive over relaxation, conjugate gradients, multigrid, parallel multigrid. And this is also on a logarithmic scale. So we're seeing the same sort of exponential growth in our ability to solve problems because of better algorithms that we've seen in our ability to do it due to better hardware. And I think this is important to keep in mind as computers get bigger and bigger and more powerful. It's still important to be developing also better algorithms as we go along. And the algorithm development has been a key component of being able to solve much bigger problems today than we could back in 1970. So we don't do so much linear algebra in the codes that we're looking at, largely because these hyperbolic problems that model wave propagation tend to be solvable by explicit numerical methods where you can update the value in one grid cell based on its neighbors in an explicit manner without having to couple everything together and use an implicit method to take a time step. Other sorts of equations where you need to couple everything together to be able to take a reasonable time step where you need an implicit method, something like a diffusion equation, for example, are much more dependent on solving linear algebra. So we're fortunate that we can get away without doing a lot of linear algebra, but still there are a lot of algorithmic advances that have made a big difference over the years. And so the adaptive mesh refinement, I would say, is one of these big advances. And I wanted to show one more example of sort of the impact that the adaptive mesh refinement can have. This is some very recent work by Kyle Manley and Clint Dawson, where they did some comparisons of the GeoClaw model that Kyle's been working on with the AdCirc model, which is a code that's been very extensively developed that does discontinuous Galerkin methods. Well, I think they use the continuous Galerkin method version. They're developing a discontinuous Galerkin version. But it's been used for actual operational forecasting during hurricanes. And so they've put a lot of work over the past decade or more into getting AdCirc working well on the Gulf Coast and whatnot. So Kyle was looking at one comparison of Hurricane Ike, which hit the Galveston region in particular quite hard. So I'll show a few shots from that. One thing I should say to start with is, of course, we don't have quite as good a resolution of, well, we have the bathymetry pretty well resolved, but we don't have as good a resolution of the friction factor, which is very important in how the waves actually come on shore often. And the Gulf Coast is very complicated because there's lots of small islands, there's bayous, there's swamps. And so you have to have sort of a spatially varying friction factor in the model to get really good results. And they put a lot of work into that for the AdCirc code that we're only starting to look at trying to incorporate variable friction coefficients in our code. So for this particular run, there were only two different values of the friction factor used, one in the ocean and one sort of on the shelf here near Louisiana and Texas. And this is a sort of representation of the hurricane or the grids that were used 3 days before the hurricane hit shore. So the eye of the storm was here. And these are just showing sort of the nested levels of refinement that were used around the hurricane. And then I don't have the animation, but you can visualize that as the hurricane moves towards shore, these nested regions move with it. But what I want to focus on is the region near Galveston up here, where initially it's very coarsely resolved. But as you approach landfall, this is days before landfall, starting 3, 2, -1, 0 days. The number of grid cells at levels 1 through 7 increases dramatically about 1 day before landfall as this area starts to get resolved. And so this is a comparison of the GeoClaw and the AdCirc results at different times. Here, 18 hours before landfall, there's still, they haven't resolved around this area very much, whereas in AdCirc, it has refined grids with a triangulation, but it's a static refinement that's set initially. And so you can see the complicated bathymetry in this region. As the calculation goes along, they start to refine here at minus 12 hours, at minus 6 hours. As it's hitting shore here, you can see the storm surge, which is a very long wavelength wave that's built up primarily from the wind forcing at the surface. And you can see that they're getting reasonable comparison between the two. Here at 6 hours, the main features are quite similar, although there are quite a few differences in these smaller channels, which is, again, largely a matter of the friction factors, we think. But if you look at some gauges offshore, at least, and do comparisons of the actual gauges that were observed during Hurricane Ike, which are the solid black lines, with the AdCirc simulations, which are the dashed red lines, and the GeoClaw simulation is the dashed blue line, then they are fairly close to one another. And the big point I want to make is that by using adaptive mesh refinement, you can do this with considerably less computing power. So the AdCirc simulation is highly parallelized, so they were using 4,000 cores. It only took 35 minutes of wall clock time, but that was 2,300 core hours. Whereas with GeoClaw, I think Kyle did it on a quad-core laptop in about 2 hours, or about a total of 8 hours of CPU time. So you get somewhat comparable accuracy. Again, AdCirc is more highly tuned for this particular problem, but with more tuning, we hope that one can get similar results with GeoClaw with considerably less computing power, and again, that's mostly a result of using the adaptive mesh refinement. So these are the 7 different levels of grid that were used, and the resolution in meters, roughly, of each grid cell. So I should mention some other people who've been involved, in particular Marcia Berger, who was a student here at Stanford with me. We had the same advisor, Joe Oliger, and we were working together already a bit as students, and we continued working off and on things over the years. When we started the Clawpack project, which was about 20 years ago now, she was involved from the very beginning in putting adaptive mesh refinement into Clawpack, and she's continued to be an active collaborator. We're still working on debugging some things just this week. So she's played a big role in getting the adaptive mesh refinement in particular to work for these geophysical flow problems where we have these special difficulties. And she is the one who developed most of the adaptive mesh refinement code that's in Clawpack using this patch-based adaptive refinement. David George, I've already mentioned, Kyle Manley, and there's many other Clawpack and GeoClaw developers who have been involved in this work over the past 20 years. I won't mention everybody by name, but there's a lot of people in the geosciences who I've learned a lot from over the years and have worked with. I have a great set of collaborators at the University of Washington in the Earth and Space Science Department, and starting to work more with people in civil engineering on looking at tsunami forces on structures and various other things. So there's a lot of people who have been involved in developing this over the last 10 or 20 years. So going back to kind of the ideas of modeling, what are the points of using a model like this? Well, I think there are several different aspects that are important. One, of course, is to just understand the science better, and being able to explore different phenomena or different possible explanations, different models by trying things out with simulations can lead to better understanding of things. You can also use observations and measurements, and there's a huge amount of data that's now available from various events that can be used to help calibrate models and help understand better what's going on in terms of the geophysics of the problems. There's also, of course, applications such as real-time forecasting and warning, which is something we haven't been very involved in my group. The tsunami warning, for example, is handled by NOAA. They have Pacific Warning Center in Hawaii and Alaska, where they have big models that they've been running for many years, and they have a big database of simulations that they use to help do that warning. But we're starting to look at some possible ways that that kind of technology might be improved in the future. But in general, it's a big application of these sorts of codes potentially that in the case of a tsunami, say the big Tohoku event in 2011 off the coast of Japan, it took about 10 hours for that tsunami to propagate to California. So there was quite a bit of time to run numerical models and to warn people to evacuate from certain places. Crescent City, California, I'll mention later, is always sort of a magnet for tsunamis in the Pacific, and there was quite a bit of damage in the harbor there, for example. Hurricane surge, as we've seen, you may have several days to be doing modeling and predictions of what the surge is going to be. Of course, the prediction of exactly where the hurricane is going to go is often quite uncertain too, but predicting the surge is something that can be done in real time for those kinds of problems. Earthquakes, they're a little harder to predict much in advance, but there is a lot of work going on sort of earthquake early warning, that if an earthquake starts to happen, there's of course lots of little earthquakes happening all the time, but they would like to figure out if an earthquake is starting, can they determine from the data they collect very quickly whether it's going to turn into a big magnitude 9 earthquake or whether it's going to die out. And sometimes even a few seconds, if things are wired up properly, a few seconds is enough perhaps to stop high-speed trains or to make sure elevators stop at a floor rather than getting stuck in between floors or something. So there's interest now in doing sort of early earthquake warning where you have maybe just a few seconds of warning. One thing we have been more involved in my group is hazard mapping and looking at hazard assessment of particular regions. We've been working some with the state of Washington on doing some mapping of the coast of the Olympic Peninsula recently. And there's kind of the standard traditional way that people have done a lot of this hazard mapping is a worst case scenario or a credible worst case, sort of the worst case that is considered for the particular mapping that you're doing, which is maybe something that is assumed to happen once every 2,500 years or something, depending on exactly what standards you're following. But more recently, there's been increased interest in doing some sort of probabilistic hazard assessment for some of these problems, and we've been involved a bit in trying to develop some tools for probabilistic tsunami hazard assessment of taking some assumed probability distribution of possible future earthquakes around the Pacific, and based on that, develop an assessment of relative risks at different places in some coastal community. I'll say a little bit more about that at the end. And then that can tie into hazard mitigation and how do you do zoning or come up with better building codes. As I said, we're working now with some civil engineering people on modeling tsunami forces on structures and on bridges and using the results of these sort of tsunami models to tie into designing better infrastructure to make us safer in the future. So let me say a little bit more about subduction zone earthquakes, which are the big ones that we look at mostly. So subduction zones are where an oceanic plate is subducting beneath a continental plate. And this is happening all around the Pacific in particular, which is why we have this sort of earthquakes, the large subduction zone earthquakes that often happen around the Pacific, and also why there's a ring of volcanoes around this ring of fire. And what happens is that these plates are slowly, continuously moving, but they're sticking at the interface. And so the continental plate on top gets sort of bent as it's deformed by the slower plate, oceanic plate sliding beneath it. And then when enough stress builds up, it eventually releases, and you get it popping up, and you get a large earthquake that lifts up the entire seafloor and lifts up the water column above it, and that disturbs the surface, of course, and that results in waves that propagate outwards. It's another sort of picture of this. And in the ocean, the amplitude of a tsunami, even a very large tsunami, might be only a meter or less. But on the other hand, the wavelength can be hundreds of kilometers, and there's a huge amount of potential energy. And it propagates at a speed that goes like the square root of gh for depth h water, where g is the gravitational constant. So it's moving at the speed of a couple hundred meters per second out in the deep ocean. As it reaches the continental shelf and the shore, the head of the wave starts to slow down before the back of the wave does, so it starts to bunch up. The amplitude can increase. But when it hits shore, it can still be a very long amplitude wave, which means that it really doesn't look like a wave on shore. It looks like a flood that just keeps coming in, as I'm sure you've seen in some of the video of the tsunami in Japan, for example. So there's a number of applications of tsunami modeling. I've already talked about a few of these, but other potential uses of tsunami modeling in particular is to look at comparing different proposed seismic sources for how the earthquake actually moved, and look at the resulting tsunami that would be generated from a hypothetical earthquake and try to match that with the data that's actually recorded. And in fact, tsunami simulations are being used more and more in conjunction with seismic inversion in order to get better models of how the fault actually slipped during an earthquake and what the resulting seafloor deformation was. So there's the source inversion problem, which often takes months after an event or years. People are still talking about what was really the slip distribution on the fault. But then there's also the question of how can you do that very rapidly if you're trying to do forecasting as a tsunami is happening. Another issue that we've looked at to some extent that's a big use of these tsunami models is to do what you might call paleofluid dynamics, of looking at the remains of past tsunamis and trying to use tsunami modeling to get a better handle on what sort of event caused those tsunamis. So in particular, tsunami deposits are used to date past earthquakes. So when a tsunami comes on shore, it carries with it typically a lot of sand and marine microorganisms, and then as it recedes, those settle down, and you're left behind with this sheet of material that then gets buried under dirt, and then years later another tsunami comes in, and so by doing core samples, they can date past events. And tsunami simulations can be used to try to help gauge where those tsunamis might have come from and how big the earthquake was that caused those deposits. So this has been used in particular in helping to understand the Cascadia subduction zone, which is the big subduction zone that goes from Northern California up to British Columbia, which has been quite quiet for the last 300 years. So a lot of people, even in Seattle, have never heard of this subduction zone and don't realize that we have magnitude 9 earthquakes there. But there was one on January 26, 1700, and they happen, according to these tsunami deposit records, they happen every 500 years or so on average. And so it's inevitable that there will be another one sometime in the next few hundred years, hopefully not too soon. So this was actually sort of discovered that this fault zone was still active and had fairly frequent earthquakes on the geological timescale only in the 1980s or so. There was this earthquake in 1700, which was well recorded in Japan, but I guess it was known as the orphan tsunami because although they had records of the tsunami, they didn't really know where the earthquake was that caused the tsunami for many years. And Brian Atwater, who's at University of Washington and works for the USGS there, and several of his colleagues, mostly in Japan, kind of pieced together evidence and looked at some of the geological remains of tsunamis on the West Coast and deduced that this particular tsunami had originated from the Cascadia subduction zone. And this is a picture of one of these sort of collections of records of tsunami deposits. This is a lake near the coast in Oregon, Bradley Lake, that has been inundated several times by tsunamis that have laid down layers of sediment. And this is at different points in the lake. Digging down, they can find up to 17 different layers going back 7,300 years of past tsunami events. And they can kind of correlate between different locations, events that, or deposits that were from the same event by looking at things like radiocarbon dating of some of the material, or looking also at layers of ash from various volcanic eruptions that they can date by other means. And then they can correlate what they find at one place in Oregon with what they find in California or in British Columbia, and they can tell which of these events were very large magnitude 9 events that affected the entire subduction zone, for example. So that's how they have an idea that these tsunamis happen every 500 years on average. So as I said, models are never right, so we have to be sort of skeptical of any results that come out. And so a big question to ask with any sort of modeling of this sort is, how do you know your results are at all correct? So there's verification and validation that we have to pay attention to, which these terms are sometimes defined as, are we solving the equations right, and are we solving the right equations? So first you need to check that whatever mathematical model you think you're solving with your computer algorithm, you're actually converging to the right solution. But even then, your mathematical model isn't right, so you have to compare what comes out of your computer code with the real world and compare with observations or measurements from past events or laboratory experiments or something like that. And benchmarking is part of this. As Eric mentioned, the GeoClaw code, we went through a benchmarking process, something called the National Tsunami Hazard Mitigation Program that supports a lot of tsunami research and that sort of certifies codes as being reasonably accurate for tsunami modeling, for doing some of this government-sponsored modeling work. So you'd like to compare also with other codes and make sure that we get similar results. There's also uncertainty quantification, which is increasingly being mentioned along with V and V, which relates to the fact that whenever we do a simulation of these large-scale simulations, we know we're not going to get the right answer, but we would like to somehow quantify the results with maybe old-fashioned error bars, but also more and more with some sort of probabilistic description of the output based on the fact that we know we don't know the input properly. We don't know exactly what the next big earthquake is going to look like, but maybe we have some probability distribution of possible future events, and we'd like to plug that through the model and come out with some distribution of possible inundation patterns that could result. And then reproducibility, as Eric mentioned, that's something that I've been kind of pushing in computational science in general, and in particular in all of this sort of hazard modeling work. I think it's very important that we can go back and ensure that we used the version of code we thought we did, and that we can reproduce the results later if we need to, and that other people can reproduce the same results that we got by using our code. So we've been trying to keep everything that we do under version control, and our software development is all done openly on GitHub, and anybody can issue a pull request if you find a bug or something or raise an issue. So we've been trying to work in ways that will make it easy to go back and reproduce what we've done in the future. So let me say a little bit about validating this tsunami code in particular. So this is the Tohoku event from March 2011. This is 3 hours after the earthquake, when the wave has spread out from Japan into the Pacific. The points here that have numbers next to them are what are called dart buoys, which are, well, the buoy is floating on the surface, of course, but it's tethered to a pressure gauge on the bottom of the ocean that's sensitive enough that it can measure the pressure of the water above it and determine the depth of the water as a result, accurately enough that you can see the tide rising and falling, and you can also see a tsunami as it goes by in the record. So for this particular event, there were a number of these dart buoys that were active and that recorded the event, and each one of these buoys has its own web page. All this data is freely available on the web. You can go and you can download data from any given time period that you want, or look at it in real time, what's going on. And what you find if you download it from one of these buoys is something that looks like this, and the big oscillations here are just the tide rising and falling. And the noise that you see in here is the tsunami going by. And this is on a scale, this is 5,262 meters, so it's in the deep ocean. And the variation here of the tide rising and falling is plus or minus 1 meter or so. And the tsunami, you can see, is sort of at the same scale. So it's a little hard to see here. So if we blow up the time around the tsunami, it looks more like this. And then if you remove the tide signature from that, you get the tsunami itself as it goes past this particular point, looking like this. And notice that this was a very big tsunami, but this is only 0.6 meters above the tide. Actually, this is the main tsunami wave here. This noise that you see before is actually the seismic wave going by, which travels through the Earth much faster than the tsunami does, and the resulting noise behind that sort of. So if you compare the actual recorded data at these 4 locations I showed, which are the red curves after detiding them, with what comes out of the GeoClaw model, for example, or I should mention there are numerous other tsunami models that are being used by other groups that have also been certified by the same benchmarking process. And many different models do a good job of matching this sort of data quite well. Of course, it also depends on what model you use for how the seafloor moved and what the slip on the fault plane was, and there are still several sort of competing models for what exactly the seafloor motion was. But at one point, we did a study of about 10 different models and compared these sort of results, and this was one of the better ones showing here. Let me show you just one more example with focusing on the adaptive mesh refinement aspect again. So this is the resolution we're using over the ocean where nothing's happening. It's a grid size of 2 degrees, which is about 220 kilometers. So these are very big grid cells. And then there's a refined patch here, a level 2 patch, and a level 3 patch. Later I'll add more levels, but we're going to zoom in on Hawaii, which is right out here, which is not at all well resolved, but as it goes along, we'll see Hawaii appearing down here. But for quite a while, we're just using these 3 levels. And notice this is 5 hours after the earthquake, but it was only 4 minutes of CPU time, and this was run on a single core of a laptop. So it doesn't use much computer time to compute propagation across the ocean on a grid that resolves that perfectly well. But then once you get close to Hawaii, we start putting in additional levels here, and then eventually we put in more levels near Hilo Harbor here. And at this point, we're down to a resolution of 1/3 arcsecond, which is about 10 meters on the side on these finest grids down in Hilo Harbor. And so the total computing time is close to 5 hours, but almost all of that time is once you zoom in on the region that you really want to study, and it depends on the resolution you have there over the time period that you want to look at it, how much time it's going to take. Another thing we've been looking at lately is comparing not only the depths at different points, but also the velocities. And it turns out that around Hawaii, during this 2011 event, there happened to be a number of gauges in the channels between the islands and in some of the harbors that measured the velocity. They were studying the currents among the Hawaiian Islands, and those picked up the currents due to the tsunamis. So you get very sort of noisy data when you look at the current. This is on the approach to Hilo Harbor here, and you can see it's fairly quiet until the tsunami comes along. And this was a station where there were actually several different current gauges at different depths at this one point. So there were a number, I think about 20 different gauges around the islands that were active during this event. So we looked at a number of these to try to validate our code against not only the depths, but also the currents. So this is zooming in on Honolulu Harbor in this case, which is up here. And first, this is looking at a tide gauge record. So there's a tide gauge in Honolulu Harbor, which is right here. And here the black dotted line is the observations after removing the tide again. And the red curve is the GeoClaw simulation. And again, getting the depths accurate is relatively straightforward for most of these tsunami codes, assuming you're resolving things well enough and solving the equations well. The shallow water equations do quite a good job, but there was still quite a bit of question about whether currents would be modeled as well. So we also looked at one of these current gauges out here. At this point, there was actual observations taken. We put in a synthetic current gauge here just to show that the current gauges have a lot more variation from one location to the next than the depth does. If you think of this wave coming in, the surface elevation goes up and down pretty much equally over the scale of a harbor, say, but the currents could be very different. You could have strong eddies in some areas and other areas that are very still. And so if you start looking at something like the current velocities at particular points, it becomes much more sensitive. So this is the actual sort of data that came out of one of these current meters. And again, it was at several locations, but we depth averaged, since we're using depth average shallow water equations. And the black line here is the actual observation, the magnitude of the speed. The part that's highlighted in red is just a 5-hour window around when the tsunami actually arrived. And this is the same data, but plotted in the UV plane. So in the horizontal, well, east-west and north-south components of velocity at this particular point. And what's interesting here is that the black part, the original sort of tidal currents going in and out of the harbor, are moving in one direction, but the tsunami current that came in is moving almost orthogonal to that and has much larger amplitude as well. So at this particular point, the main tidal currents were sort of going parallel to shore, but as the tsunami kind of wrapped around Oahu and came in here, it was coming in much more normal to the shore. So you get very different sort of flow patterns. And then what's shown below is again, these velocities, but now over this shorter time window of 5 hours or so. The black curve is the U velocity, and down here the V velocity as measured at that gauge, and the red curve is the corresponding measurements from the GeoClaw model. So even for the velocities, one can get fairly good accuracy out of these sorts of models. And this is the same data looked at in the UV plane, so that you can see that in addition to the amplitudes being about right, the direction of that this wave is coming in was also about right. And this was a study we did just to show how much variation there is between 2 points that seem to be close together on the global scale. If you look at these 2 points and you look at the surface elevation as a function of time, so these are both out of the simulation, but just looking at 2 different points, they track each other pretty well. But if you look at the maximum or the flow speed at these 2 points, at this gauge where it was actually measured is the red curve down here. At this gauge up here that we put in the computation, you have an order of magnitude larger velocity. This gauge we put in here was sort of in the entrance to the harbor here where you could have quite strong flows, whereas this one was out away from shore where there wasn't quite as strong a flow going into the harbor. So I point that out because that makes it, to me, more impressive that these tsunami models can actually capture the velocities quite well at particular points because it's very sensitive to exactly where that point is, what sort of velocity you'll be measuring. So I mentioned Crescent City. Let me just say a little bit about what we've been doing there. We've been working on a project that's funded by Baker AECOM, a consortium of companies that have been funded by FEMA to do some mapping of the California coast and to do a pilot study of probabilistic mapping in the area around Crescent City in particular. And so Crescent City is an interesting place for tsunamis because there's this Mendocino fracture zone out here where there's a ridge which tends to focus tsunamis right into the Crescent City area. So if you go back to this figure I showed before, if you look right up here, it's sort of darker colors in the part of the wave approaching Crescent City. It acts as a waveguide, basically. The wave is moving slower on top of the ridge than on the side, so it's kind of folding in on itself. And so you tend to get very strong tsunamis in Crescent City. And they have a current evacuation map, which is based on a sort of a credible worst-case tsunami simulation that was done some years ago. This is the harbor region and the main downtown area. This is the evacuation zone. But the idea of our study was to try to do a probabilistic map instead, where rather than having a single map, you would have, for example, a map with the region that is expected to flood with annual probability 0.01, which is like a 100-year flood map, as FEMA calls it. Or if you look at an annual probability that's smaller, 0.002, then you're getting much more impact from these once every 500 years or so Cascadia subduction zone events, and there's a much larger region that can be expected to flood with probability 0.002 each year. So producing these sorts of maps requires doing lots of tsunami runs, and it also requires having a lot of information about what's the right probability distribution of possible future earthquakes, which is really the hardest part of this project, is trying to figure out what's a reasonable set of possible tsunamis to run. So we ran a number of events from Alaska, Kamchatka, Japan, Chile, but then the big one is, of course, the Cascadia subduction zone and trying to figure out exactly what the right probability distribution for possible slip on that fault zone is. So this is something that's still very much ongoing work. This is Crescent City Harbor during the March 11th, 2011 Tohoku event. A photograph of the currents coming in at one particular time. It sort of came around the breakwater here and into the boat harbor. There was something like $20 million of damage in Crescent City Harbor due to this tsunami. They're doing a big major renovation of that harbor now. So we tried also doing our simulation for this event here. I don't have a great picture, but this is sort of the coming out of GeoClaw, what the maximum velocity was over the whole simulation at each point. So it isn't a particular time instant, but it's sort of looking at the maximum flow velocity at each point. And we tried to sort of line it up here. So here's the breakwater where the water comes around, and then it swirls around in here. And you can sort of barely see there's some numbers on here. This is from a thesis of Amanda at Meager at Humboldt State, where they estimated the flow velocities to be 4 or 5 meters per second, 3 meters, 2 meters per second, 1 meter per second. And the scale here is also, this is 4 to 5 meters per second, the red and orange area. So you get, again, similar flow velocities and similar patterns of how the flow comes into the harbor. So this is another sort of active area of research in tsunami modeling, is trying to model currents in harbors and the effect on infrastructure, and ultimately doing probabilistic modeling of currents as well as flow depths. Okay, the final point that I wanted to make, I think, is that these hazards are often coupled. And as an applied mathematician working on hyperbolic equations, I, of course, see that there's lots of connections between these problems because the mathematics that's involved in solving these equations is often quite similar. And so I think for people working in my area, it's a very rich area of problems. But I think in general, we have to look at how these different hazards interact with one another. So of course, earthquakes cause tsunamis, but also landslides can cause tsunamis. There have been some cases where very large-scale landslides have caused tsunamis that have killed people. Of course, earthquakes are often the trigger that causes the landslide. Submarine landslides along the continental slope often happen, sometimes hundreds or thousands of them following one of these big subduction zone events that themselves cause tsunamis. Landslides also cause seismic signals, as I mentioned, that it's interesting to look at that coupling. Volcanoes I haven't talked about, but there's all sorts of flow problems that come out of volcanoes, pyroclastic flows, debris flows, ash plumes in the atmosphere. Of course, volcanoes can also cause tsunamis if it's an underwater volcano or if there's a flank collapse on an island volcano or something. And then as a tsunami or a storm surge comes inland, it eventually becomes a debris flow. If you saw the videos of the tsunami in Japan going over the Sendai Plain, it wasn't just water, it was a very thick debris flow with all sorts of debris in it. And so coupling the tsunami model together with debris flow models ultimately will be important. And as I mentioned, this also has to be coupled with civil engineering, policy management, and a variety of other fields. So one thing that we're doing in this direction at the University of Washington is we have one of these NSF Hazard Seas grants. That's a big interdisciplinary grant that just started up this year called the M9 project. The focus is on modeling a magnitude 9 Cascadia subduction zone earthquake and the resulting tsunami and the effect on infrastructure and hazards and resilience. And it involves faculty from a number of different departments and schools at the university. We've even got people involved in sort of psychology of how do you communicate probabilistic risks to the public and to emergency managers, and how do you impact public policy as a result of some of the modeling that's being done. So I think there's going to be a lot of interesting things coming out of this. So to summarize very briefly, there's a huge number of challenging, very interdisciplinary problems where there's still lots of work to be done. There are pretty good mathematical models, algorithms, and software for some of these problems, but there's no shortage of problems where much better tools are needed. And for people here who are looking for projects doing computational modeling, this is a great area to get into. And I hope that more people will get involved in doing sort of hazard modeling. I think there's a lot of important problems that still need work. So if you're interested in reading more about some of the things we've been doing, we had a paper in Acta Numerica, sort of a review paper of some of the tsunami modeling capabilities of GeoClaw and how the adaptive mesh refinement works. Another paper that's more on the sort of software side of it, with some more validation studies and whatnot. And then all of these National Tsunami Hazard Mitigation Program, tsunami benchmark problems that were done were written up for many different models, not just ours, in a report that was published a couple of years ago. And you can find all of these on our website. And in many cases, the code that goes along with the papers should be there too, and hopefully still runs. So, thank you. So I'll be happy to take questions if there are. Yeah, Greg?
Yeah, you mentioned in one of the important trends uncertainty quantification, that's how you put it.
It is.
properly at low probabilities. So it would be even more challenging to communicate uncertainties. How do you see that going?
Yeah, I think that's one of the big challenges. The question was, how do we sort of address this challenge that it's hard enough communicating probabilistic risks? How do you communicate the uncertainties and the probabilistic risks? And I think that's something I hope we'll be looking at in more detail with this M9 project, because I think there's a lot of work to be done in just how do you communicate those risks to the public or even to emergency managers. And we've talked to a number of people sort of from the emergency management side who wouldn't know what to do with a probabilistic map. They want a single evacuation map that tells what to do if there's an earthquake. And trying to interpret a probabilistic map may be hard enough, but then explaining that, well, the probabilities maybe don't even mean anything because we had to assume some probability distributions that probably weren't right. And so how do you try to communicate that some areas are at much more risk than others, which is certainly true and which we can say, but not get too much into quantitatively saying, well, this particular intersection in the city has a 0.0036 probability of flooding next year, when we obviously can't say anything like that with any certainty. And I honestly don't know what the best way to do that is. And if there are people here who have thought about that problem or are working on that, I'd be very happy to talk with you about it. But that's certainly one of the big problems, I think, in trying to move into probabilistic forecasting for these events. Yes?
Yeah, for say like the debris flow examples that you showed at the beginning, or the mudslide, I mean, how much of that is sort of strict forward modeling and how much sort of inverse problem is involved there? And if some of the latter, what sort of data are you actually assimilating to get results?
Right, so I can't say too much about the debris flow code since I haven't been involved directly in that, although I do know for this OSO slide of a few weeks ago that a priori they wouldn't have thought that the flow would have gone nearly as far as it did, and they had to make it much more mobile than they would have expected in order to get results that sort of matched with what was actually observed. So I don't know the details on that, but I know there was definitely some fitting to the actual observed data. But then they could use that, they were using that to some extent in the aftermath of the event to try to figure out where some of the houses might have gone to that they were still looking for, and being able to have a model that kind of matched what was seen at the final time allowed them to look at where things were moving during the course of the landslide. In terms of the tsunami modeling, there are certainly some tunable parameters in the model, but there's actually relatively few. So one of the big ones in terms of inundation is the friction factor. So in the shallow water equations, we use a sort of Manning friction coefficient in the momentum equations that has some coefficient times some term that gets very large as the depth gets small. And so as the flow gets very, very small, this friction term kicks in, and at some point it's going to stop the flow. And there's tables of what a reasonable Manning coefficient is to use for various kinds of surfaces, for sand or gravel or brush or trees or whatnot. Of course, you really don't have just one sort of topography. You have a combination, which is why we're starting to look at putting in variable Manning coefficients. But still, that's kind of a tunable parameter to some extent.
So is it sort of still done for these kinds of models? Is it more done manually, or is this the kind of thing you've got some kind of, whatever, adjoint-based data assimilation procedure?
So for the tsunami modeling, for that aspect of it, we're typically using, there's a standard value of the Manning coefficient, 0.025, that people typically use, which is flow over gravel or something. It's sort of a worst case of a tsunami coming in on bare land. And also, I should say that the topography that we use on shore doesn't have structures in it. So it's the bare earth topography. And so there's a lot of questions about, what's the accuracy of this inundation model compared to what's really happening when you have structures. And of course, the structures may get knocked down, and then it becomes a debris flow and becomes much more complicated. But in terms of that sort of modeling, we haven't been trying to match results by fiddling with that parameter. We typically use a particular parameter, or if we want to do a run with a more conservative run, maybe we use a smaller value of that parameter or something. But we haven't been doing very much data assimilation of any sort in the tsunami code. We have been starting to look at adjoint methods for doing the adaptive mesh refinement. I have a student now who's starting to look at using adjoint error estimation, because the tsunami, if a tsunami is coming across the ocean from Japan towards Crescent City, of course there's the direct wave that you know you want to resolve, but there's waves going off in other directions that probably you can ignore, but maybe they reflect off of Hawaii and become important at some later time. And so you'd like to sort of trace back using the adjoint equation to figure out what are the regions that you really need to refine in order to capture the waves that are coming in on the particular harbor of interest, for example. But the tsunami modeling, there aren't really very many free parameters. I guess the biggest uncertainty is really the seafloor motion that generates the tsunami. And there, you know, for past events, we use the best inversions that seismologists and other people have put together, often using other tsunami models to do the inversion, perhaps. But that's, to a large extent, the biggest uncertainty in these tsunami modeling problems. Yeah.
Assuming that we know exactly what sea level rise might occur, how long do you think that these tsunami hazard maps will be valid?
Yeah, so in terms of sea level rise, well, yeah, if sea level goes up substantially, then the tsunami mapping would presumably have to be redone at the higher sea level. I guess, so when we talk about something like a 100-year flood or something, that, again, has to be interpreted as sort of a 0.01% probability of occurrence in the next year that's valid with the current level of sea level. And if sea level changes significantly, then things would have to be redone. But, I mean, it would take, when we're looking at these big events like a Cascadia subduction zone, magnitude 9, which is, 10 meters of water coming in, a few centimeters of rise obviously isn't going to make any difference in that. So it depends on the scale of the event you're looking at and how much sea level rise we're having.
Okay, if there are no further questions, please join me in thanking Randy and then join us for
Thank you.
the